So in our last lesson, we looked at scatter plots and how to apply a line best fit to them to create a mathematical model for predictive purposes. The challenge we came across, however, was that we all had different models, different equations, because it was a by eye method. So in this lesson, we're going to look at a technological way to actually place the line of best fit so we all have the same line, the optimal regression line, we call that. And the method we're going to use is something called the least square methods. And the way this method works is, look at this diagram here. We're going to place the line such that the residual, which is the vertical distance between each point and the line, so this distance right here is a residual. Now, if the dot's above the line, it's a positive residual. If the dot's below the line, it's a negative residual. And of course, we're going to have all kinds of dots. Well, our objective is, with these dots, that the positive difference, when we add all these positive differences up, will be balanced out by the negative difference, so that the total residual comes out to 0, or as close to it as we possibly can get. Okay. That way we're not by eye guessing anymore, we're mathematically placing it so that the answer, the residual, comes out to 0. Okay. To do this, well, we have this beautiful fancy equation that actually does the math for us. The equation of the line of best fit is given by this lovely thing up here. Now most of these symbols are ones that we know. We have the mean of y and the mean of x, we know those. Yesterday we talked about this one, those are covariance. We did that, we calculated that yesterday when we were doing R. And then this one, of course, is the standard deviation of x. And it's squared, so it's actually the variance of x, if you will. And now the good news is, we don't have to do this by hand. We could do it, we could calculate all these things. They're not hard to do, it's just really time consuming. So we know that we have some technology that we can use that will help us do the problem. So let's take a look at yesterday's example. Same question, but we're not doing this by hand anymore. We're going to use our graphing calculators. So age and mean word length. I want to find the equation of the line best fit. So here's our instructions. We got to create a scatter plot. To do that, taking our graphing calculators out, we're going to turn it on. That's a good start. And then we're going to enter our data like we always have. Stat, edit. Oops, edit. Okay, but we have two sets of data this time. So we have to enter data in L1 and also in L2. So I'm going to put all the ages in as my L1s in my first list. I'm going to go over to L2 and put in the corresponding Ys. 6.1, not 61. Okay, make sure I have the same number of things in each column. Scan quickly to make sure I didn't miss any decimals. That's often a mistake. Okay, so I'm good to go. To make a scatter plot, it says here we're going to go to second y equals, stat plot, the same way we did histograms. So second y equals. We're going to turn it on. Okay, right now it's turned off, as you can see. Let's turn it on. And the first one is the scatter plot, which is what we want. When we did histograms, we used to have to use the window adjustment, but the nice thing with scatter plots is we can use the zoom button. So we're going to go to zoom, and we go all the way down to number 9. So zoom stat. Or if you will, just press zoom and then 9, and it does it for you. And there's our scatter plot. Perfect, just the way we want it. Exactly what we saw on our page yesterday when we did this by hand. But we don't want to just make the graph, we want to analyze the graph. So, second half, finding the line of best fit. And to find our line of best fit, the first thing I need to do is turn my statistical diagnostic on. When you clear the memory in your calculator, it always turns this off. Okay. So the first thing I have to do is go to mode, and then go right to the bottom, way down here. And it says stat diagnostics. It's turned off.
Can I have your attention, please?
Okay, we want to turn it to on, so we're going to highlight on. Okay, we need to do this when we do a scatter plot regression analysis. Okay, make sure you turn it on. We're then going to go to stat, over to calc, and I want to do number 4, the linear regression, making a line of best fits. We'll go down number 4 or press number 4, either way works. Make sure your list L1 is your X's, which it is. L2 is our Y's. We don't want anything else in these things. We don't have any frequencies. We're going to go right down to calculate. Okay, and there we go, our line of best fit. So all the things we did by hand yesterday and had different answers for, we can now do the graphing calculator and get the exact same answer for. My line of best fit is y equals 0.517x plus 1.93. Notice at the top it gives us the model format. So this is my format up here, and I just fill the right numbers in the right spots for A and B. Okay, that's way faster than doing it by hand, right? And more accurate because we all have the same answer. So I'm going to get you guys to try one. So our next example, right here. Hey, the coach of the Statsville football team wants to determine if there's a relationship between how fast players run and how far they throw the football. And here's the results. So we're going to create a scatter plot. We're going to classify our correlations. We're going to say positive, negative, weak, moderate, strong. We're going to do our linear regression, find the line best fit, and the correlation coefficient, and then we're going to explain what they mean. So first thing we need to do, let's clear our memory rate off. Second plus 7, 1, 2. Okay, stat, edit. Let's put our data in. Now I'm putting the first column in as my x's. It doesn't really matter, really, which one you put in your x's. I just suggest that first one goes first. It makes more sense. Okay, be careful with your decimals here. Make sure you have the decimals. Okay, we'll go over to the second column. We want to put in our data for throwing distance. Make sure we have the same number of things in each column, which I do. My two bottom things are both blank. Okay, I'm going to turn my stat plot on. So highlight on. I'm going to press zoom 9, and there's my scatter plot. So it's not pretty. It looks like it's going generally this direction, but I got these dots that are kind of all over the place, right? So I'm going to say that's a negative and probably a weak one. So part A, this is a weak negative correlation. I'm suggesting weak just based on my by eye view of this. We can figure it out mathematically when we do our linear regression. So stat, calc, number 4, go all the way down to the bottom. And what do I get for linreg? Y equals negative 2.39 x plus 51.19. And notice that the R value didn't come up, and it wants me to find the correlation coefficient. The reason my R value didn't come up is because I didn't turn on my stat diagnostics. So if you ever get to a point you're like, oh, why am I not getting R? Because you forgot to go to mode and go down to stat diagnostics and turn it on. Every time the calculator is cleared, it automatically turns it off. So you got to remember to do that, okay? Now if we go back to stat, calc, linreg, and do it again, we'll get R. R is negative 0.45. Just to point out, whatever your slope value is, if it's a negative, this should be a negative. If it's a positive, it's a positive. So mathematically, yes, it's negative, but it actually turns out it's kind of a moderate correlation. It's halfway into the moderate zone. Hey, part C, explain what the values mean. Well, there's two values in this equation. 51.19. It's a theoretical value. Basically what that means is it's my y-intercept, my starting point. Okay? 51.919 means is the throwing distance for a sprint time of 0 seconds. It's our initial value. So theoretically, and it's totally theoretical, this is not a practical number because no one has a sprint time of 0. But theoretically, if you were so fast, your sprint time was 0, you should be able to throw it 51.19 meters. It's a number, but it's not really a useful number. The one that really is, however, is the other one. A negative 2.39, which is really the slope number. So remember our slope was calculated by a rise over a run. In other words, our meters divided by seconds. And in particular, this is 1 second. So negative 2.39 represents a drop of 2.39 meters for every additional second. 1 second of running time. So why is that important? Well, I can use that for predicting. So basically, if you're slower, every second slower you are, your throwing distance is shorter by 2.39 meters. So it's kind of a useful number. I can say, well, if you can throw, if you can run for, sorry, if it took you 10 seconds to run something, well then if you're an 11-second person, you throw shorter. You don't have you can't throw quite as far. Okay. All right. So our next idea, interpolation and extrapolation. So why do we actually create models? We use them to make predictions. And we call that interpolating and extrapolating. But predictions are only really good if your model is good. So our basic rule is if our correlation coefficient is moderate to strong, so it's got a pretty high number, I would say 0.7 plus at least. I'd prefer more like 0.8 or 0.9. Then predicting our points could be very accurate, okay, as long as they're between points that we already know. And we call that interpolation. However, when we extrapolate, going outside the range of data that we know, well, we don't know what's going to happen next. Maybe we're going to run out of room. You can't run that slow. You can't run that fast. We can't throw that far. We don't know what's going to happen. So any results we generate are going to be unreliable automatically as soon as you go to the range that you don't know. Also, if the data contains outliers, well, our predictions are going to be affected because our model's been affected. Okay? There is no mathematical test on a scatter plot for an outlier. So you can't use your whole Q3 minus 1.5 IQR. That won't work here. Okay. What you have to do is you have to look for a vertically distant point, something that's got a really big residual. So this point here is really high above the line of best fit. It would be an outlier. This dot is far away from the rest of the dots this way, but it's not an outlier because it's following the pattern. The pattern is going down to the right. Okay, so it's all about the residual size to decide on outliers. And as I said, there's no right way, wrong way to saying which ones the outliers and aren't. It's based on your by eye idea of is it too high or too low. So let's take a look at one more example here. Okay. Oh, one more thing. If outliers are present, examine it with the outlier and then recalculate it without the outlier to see what effect it had. Was our model good or was it bad? So our last example here says, using the previous data from the stats football team, state which two data points can be identified as outliers. So if we go back to our graphing calculator and turn it back on, and go back to our graph, which was zoom 9, you notice that most of my dots are going this way, except for this dot and this dot. Well, I can figure which ones those are by using my trace button. So when I use trace, I'm going to use my left and right arrows. It's going to go from dot to dot in the order that they're entered into the calculator, not the order they are on the screen. So I have to go dot to dot till I find the right dot. There's one, 7.55 and 40. That is definitely an outlier. I'm going to write them down here, okay? 7.55 and 40. And if you keep going dot to dot, the next one is 7.75 and 26. So to remove an outlier, we have to go back to our data, stat, edit. And then we have to go down the list till we find those. So 7.55. I want to delete that one. So I'm going to use the word delete right at the top. Right here, delete. And then I'm going to go over and delete the 40 that goes with it. Okay, then I go back to my list and find the next one, 7.75. Delete, and the 26 that goes with it. Okay, so we're doing part B right now. Remove them and repeat the regression analysis. Find our new line of best fit. Okay, so we're going to take them out. Let's do our stat, calc, 4. Everything's still the same, but we have a brand new line of best fit. What is our line of best fit? Well, y equals negative 2.19x plus 49.0 basically. And our r value, which was kind of weak, moderate-ish, it's improved to a negative 0.665. It's still in the moderate range, but it's way higher than it used to be. Okay. So let's answer some more questions. What might the coach conclude from this analysis? Well, if you look at the pattern, the fact that it goes down and to the right, zoom 9. Oops, I missed the zoom button there, zoom 9. You can basically say as sprint times increased, which was my x variable. Throwing distances decreased, which was my y variable. It's going down to the right. Okay, so if you're a slow athlete, you're probably a bad thrower, it looks like. Basically, there are some outliers that didn't follow that. And use the equation from part B, that's the one we have right here, to estimate what would happen if someone has a sprint time of 7.5. So we're going to do a quick calculation here. Okay, so using my line of best fit, my model, I can say y equals negative 2.19. We're using an x value of 7.5 seconds. And we had plus 49 at the end. What does that give us? We type into our calculators, we end up with 32.73. And this is our throwing distance in meters. So basically I found an additional point. I've interpolated. It's not a point on my graph, but it's a prediction that I can make based on my graph. Let's try E. If a player is able to throw a distance of 38 meters, what sprint time should be expected? Again, this is using our equation, but this time I'm saying I know the distance. Let's solve for our sprint time. So we'll do our math. This is kind of as hard as the algebra gets in this course here, just rearranging stuff. And I'll divide it out. And 11 divided by 2.19 comes out to approximately 5.07. So that's how long, how fast they are. Approximately 5.07 seconds, if they can throw 38 meters. Okay, would you expect that the estimations in part D and E would be accurate? So, what we're trying to get across here is the idea is, are these values within the range of values that I know? So, do I know anything about throwing 38 meters or running 7.5 seconds? So we go back to our data. Okay, 7.5 seconds fits between two known values. Throwing 38 meters fits between two values. So yes, this is interpolation. So my answer to this question is, well, this could be fairly accurate. However, how strong was our model? The model value is right here. It's not a great model, it's moderate. We prefer strong. So despite being interpolations, these values are not very accurate, as the model is not all that strong. Okay? We want a strong model to make good interpretations. Okay? At least 0.75 or higher is what I would say. Okay? All right, that's the end of regression. Homework. We're using our graphing calculators today. Make sure we can use the graphing calculators. Technology is a key part of this course. If you're stuck with some things, come see me.